All right, what is up, everyone? The setup is a little bit different today, um, just because I wanted to kind of play around with it and see what turned out better, what didn't turn out as good. So, do let me know what kind of style you prefer. But today we'll be going over round 723 solutions. I'll go through A through D, and that includes both subtasks of C, although I'll probably only go over how I solved the second subtask, because when I did this contest officially, I solved both of them at once. And I feel like the second subtask for C it's simple enough to where I don't really have to explain the first one. So yeah, without further ado, let's do it. All right, so problem A is okay. If you don't know how this works, basically I'm going to assume that you've read all of these problems already. That way it just saves some time. So that I don't have to explain how the problem works. If you don't know what these problems are, I'll put the link in the description, and that way you can look at the problems and think about them for yourself before you watch my solutions. So problem A, the important thing to notice is that all of the values in this array are distinct. So for example, if our array, keep in mind, also has an even number of elements. If our array was, for example, 7, 1, 3, 5, 2, that's just a random array I just came up with. Oh, okay, that's an odd number of elements. Let's add a 4 in it as well. Yeah, it doesn't really matter just what these elements are. They just have to be distinct. And the reason why the fact that they're distinct is so important is because if we were to think of, we want to first sort these values, right? Because we want to find some permutation of this original array such that the condition that no element is the arithmetic mean of its neighbors is satisfied, is a thing. So pretty much what we do is we first sort these values. So in this case it'd be 1, 2, 3, 4, 5, 7 in this test case. And then what we realize is if we put these first half of numbers into the odd indices and the second half of numbers into even indices, this means that any number, the two neighbors of any number will either be strictly greater than the original number, or they'll both be strictly less than the original number. So for example, if we know that if A is a middle number and its neighboring numbers are B and C, with this alternating arrangement, we can either guarantee that A is strictly less than the minimum of B and C, or we can guarantee A is strictly greater than the maximum of B and C. And either way, this can guarantee that A is strictly less than B plus C over 2, or we can guarantee that A is strictly greater than B plus C over 2. So this is how you solve problem A. You just sort these values and then put the smaller values on odd indices and the even values on larger indices. So yeah, that was pretty simple. There were a lot of solves in that problem, so I don't think that was too much of an issue. But let's move on to problem B. Now problem B I think was it was a little bit trickier, but it just requires a few mathematical observations. So when you have these type of problems where you want to think of representing some number as as a sum of some other numbers, the first thing I realized was, for example, if you had something like 1, 1, 1, 1, 1, 1. So this is divisible by 11. So, okay, well that's not right terminology, but okay, so if we took 4 1s, keep in mind that this is divisible by 11. And then if we took 6 1s, this is also divisible by 11. Is that 6 1s? It is. And the reason why is because if you know the divisibility rule for 11, all you do is take the digits and you take a alternating sum of the digits and then check to see if their difference is a multiple of 11. And in this case, if there's an even number of digits, then their alternating sums are going to be the same. It's like this is like 2 and 2, and then this is like 3 and 3. And then the difference of these alternating sums is always going to be equal to 0. And 0 is divisible by 11. So we can pretty much ignore any number with an even number of ones in it, because we can represent it as some number of 11s. So that's the first observation that I made officially. And then to make another observation on numbers with an even number of with an odd number of digits, my bad. The one way you could think about it is like this. So we know that 111 is a meaningful number because it is not a multiple 11. In other words, this number has to be like, this number is important because we can't represent it as some multiple of 11, if that makes sense. But we can show that any like odd digit number with more than 3 digits, so if there's like 5 ones, or if a number is 7 ones or 9 ones, so on, we can show that those aren't actually important either. And the reason why is something like this. So let's take a case where we have 5 ones. This is equal to 111, 0, plus 1, 1, right? And then this in turn is equal to 100 times 111. That's one extra one. Plus 11. Oh my god. Oh yeah. Which is then equal to 100 times 111 plus 11. And so if you realize that, so basically what this means is that this number over here can be represented as like some multiple of 11 plus some multiple of 111. And then if we had like say 7 ones, it's a similar logic. 1, 2, 3, 4, 5, 6, 7. We can say this is equal to 1, 2, 3, 4, 5, 0, plus 11. And so if we can represent this number over here as some multiple of 11 plus some multiple of 111, then we can represent this number as as some like form of these two numbers. So yeah, and note that this is just 100 times 5 ones. So with this observation, you realize that if you can represent a number as a sum of like some number of like these 1 numbers, you can represent it as a sum of 11 and 111. So in other words, you just want to check to see if n can be represented as a times 11 plus b times 111, where a and b are greater than or equal to 0 and are integers. Okay, and so from here, there's a kind of a little theorem, I guess. I think it's called like the official name is the chicken nugget theorem or something like that. But basically, if you're familiar with like Diophantine equations and how like just number theory works in general, you don't actually have to know Diophantine equations to solve this problem. I'm just trying to give like a more formal, I guess, proof on how I view this. But pretty much, if any like number sufficiently large enough it will guaranteed be able to be represented in this form. And I'll kind of reason you through why. So if we say, for example, keep in mind that the GCD, and this is GCD of 11 and 111 is equal to 1. And this is the reason why that this logic works. So if we had like some arbitrary large number, let's say it's like x, for example. Obviously, if x mod 11 is equal to 0, then x is divisible by 11, and we can just represent it as a bunch of 11s, and that will satisfy our problem. Otherwise, if it's not equal to 0, then we have to subtract 11 from it, and then we can check to see if it's like not equal to 0 or like whatever. And then we just keep on like subtracting these numbers. So for example, if this holds true, so if x mod 11 does not equal to 0, we would like think of it as subtracting 111 from it to get like x minus 111. mod 11. And because 11 and 111 are relatively prime, we only need at most, I believe, 11 iterations in order for some value of x minus like b times 111 mod 11 to be equal to 0. So this is assuming that x is sufficiently large. So we only really need to check the no case if x is somewhat small. The specific value doesn't really matter, but I believe in this case, we can guarantee that the answer is always yes if n is, I believe if it's greater than or equal, I think if it's greater than or equal to 1099, I think. It might be 1100, but either, yeah, that's like pretty much how it works. So there's a few ways you could implement this. You could just use an if statement as like kind of a math equation, or you could use really basic knapsack DP for like some small values. So if you do like DP at x where this is true if the answer is yes. If answer is yes for n equals to x. And the way the DP would work is that if DP of x is true, then DP of x plus 11 is also true. And then also DP at x plus 111 would also be equal to true. And we only have to check for like a small value of x. So I believe in my code, I actually did up to less than or equal to 10 to the 6, but you don't really need to go that high. Something like x like less than or equal to 1200, or in this case, I guess, x less than or equal to 1099 is sufficient. So yeah, that's how you do problem B. Moving on to problem C, I'll go over how you solve a hard version of C, because I think like the DP, the n squared DP that the editorial provided is pretty standard, and I don't think, and I feel like if you're familiar with DP, then that problem shouldn't be, then like the DP shouldn't be too hard to see. But yeah, let's go on to C2. So we can reword this problem as given like some like array of numbers. So I'll just take the input. So if I do 4, -4, 1, -3, 1, -3, we want to figure out what is the maximum number of potions that we can take, or I guess maximum number of integers that we can take, such that if we were to take the subsequence and construct a prefix sum array, none of these prefixes would be less than 0. So for example, if we were to take the subsequence like 4, 1, -3, and -3, what the prefix sum array would look like, it would look like 4, and then 4 plus 1 is 5, and then 5 plus -3 is 2, and then 2 plus -3 is -1. So if we were to take this subsequence, this would be our prefix sum array. And this is not valid because this term over here is less than 0. And we want to take essentially the longest subsequence in here such that no value in this prefix sum array is equal to 0. Okay, so it's kind of tricky to think about constructing an answer, like constructing the subsequence. So instead, it might be helpful to think about starting from any subsequence and then removing elements from it to make the subsequence valid. So what I mean is, instead of solving a problem of the maximum number of potions you need to drink, you can drink, instead you could think about the minimum number of potions that you have to remove in order for no prefix sum to be negative. And so if you think about it, let's just pretend we simulate this process the way it is. So for example, if we just go through this array, over here our prefix is currently equal to 4, right? And then we drink this potion. And then over here we drink this potion, -4. And this will mean that our like current health, or just like the sum in general, is equal to 0. And so far it's so good. We haven't dipped below 0, so as of now we can still keep all of our potions. And then we go to 1, 0 plus 1 is equal to 1, so still good. And then -3, where 1 minus 3 is equal to -2. And so now we run into a problem, because our current prefix value is strictly less than 0, and that's bad. So we know that we have to remove some number in this range in order for our subsequence to still be valid. So take a moment to think about it and realize that, wait a minute, if we have if we're forced to essentially skip one of these potions, why not just skip the worst potion? So in other words, these 4 potions are essentially the state of potions, well, the set of potions that we've already visited, and we have to remove one of them in order for the sum of the remaining potions to be greater than or equal to 0. So in this case, -4 is the is like the worst potion that we've drank so far. So we would essentially take this potion out of our subsequence. So now we basically took this prefix sum, and because we skipped this potion, we want to add 4 to our prefix. And so now our current prefix value is 2, and essentially like 4 plus 1 minus 3. And so now it's fixed, and then we move on. And then we have a value of 1 over here. It becomes 3. 3 is okay. And then we have a value of -3 over here. 3 minus 3 is equal to 0, which is still okay. Okay, so with this process, we see that we removed exactly 1 potion. And this means that because we remove 1 potion, the longest possible subsequence is the length of the array minus number of potions that we remove, which in this case is 5. So I guess once you make this observation that when you ever dip below 0, you can always remove the worst potion that you've drank that hasn't been removed yet, and that can only make your answer strictly better. And that's a key observation that you make here. So how would you go about implementing this? Well, you want to think about a few things that your data structure would want to do. So the first thing that it wants to do is you want to add a value to it. So you want to add something. And then another thing you want this like data structure to do is you want to be able to get the minimum value out of all the numbers in this data structure. So you want to get min. And then the third thing that you want it to do is you also want to remove the minimum value. So if you're familiar with basic data structures, if you want to add a value, you want to find the minimum, and you also want to remove the minimum in a good runtime, you want to use a priority queue. So yeah, just use a priority queue. The implementation is very simple. But yeah, honestly, I thought this problem was easier than B in my opinion. Like even the harder version was easier than problem B. But yeah, that's just my opinion. Yeah, that's pretty much how problem C works. And this solves the hard version because it's n log n runtime. Okay. So time for problem D, kill Anton. Let's see. Okay, so problem D, pretty much you can generalize this problem as given some array of integers, you want to find some permutation of these integers such that the inversion count is maximized. And so in the problem statement, it gave like a wording as the minimum number of moves that Anton would need to fix his DNA is the number of like moves he would need to swap 2 adjacent characters. And that's basically a definition of the number of inversions in the string or array, I guess. So we want to essentially maximize the inversion count. So already the first thing that you should be thinking about is, okay, what is the like what is like a way that I can use to count number of inversions in any like given array. And so you could either use like a binary index tree, or you could use like some like sort of DP, because you realize that because there's only 4 different like characters in the string, there's essentially only 4 different values that we care about. So I believe we can actually do a DP in like either 4 times n or 16 times n. Either way, it's like kind of the same thing. Or we could just use n log n bit. It doesn't really matter. All 3 of those should be fast enough anyway. But the important thing is to think about what should the final string look like in order to maximize the number of inversions from the original string. So I don't really have a good proof for this, but basically you make the observation that in any optimal string, all characters of the same value have to stick together. So for example, if we have the test case of O, A, N, T, T, O, N, we can like, these N's have to be in the same block and these O's have to be in the same block, and the A's and the T's. So for example, if we had something like A, N, N, and then like O, O, and then T, T, keep in mind that all of these A's, all of these N's, all of these O's, and all of these T's are together. And so this is like the invariant that we have to maintain when checking all the possibilities. We have to check all like possible orderings of these 4 characters, but the thing is that these blocks of characters always stick together. So I guess one intuitive way to think about it is let's assume that we have like some string that's like, I guess A. Okay, well, how did I think about this officially? Let's see. Okay, the way I thought about it was to think about how like the process of swapping 2 adjacent characters to fix a string would look like. So basically it would look like you would have like some character over here. So let's call it like X, for example. And this is like the initial string. And then, or not the initial string, the target string. And then this is like your current string over here. So if the first character in like your target string and your current string are equal, then you can essentially just ignore that character and solve the same problem for like a slightly smaller string. Otherwise, you would find the first occurrence of this character in this other string. So let's say X occurred over here. And so if this place over here was the first occurrence of X, then you have to move it over like this number of times until it hits this first spot. And so moving this over here, it doesn't change the relative order of any of the other characters before X and after X. And the cost is essentially I, where I is a location of like this X and I is 0 index. So it's like 0 less than or equal to I, strictly less than N. So yeah, that's like how this process of fixing a string would look like. So in this string over here, so it would be logical to basically try to maximize this distance like between these characters as much as possible. So if we wanted to like so let's assume that there existed some like maximum distance that we could insert X to B. So like if it's somewhere like towards the end of this array or like towards the end of a string. If it's towards the end of a string, whenever we want to get the next character of X or like a next occurrence of X later in this target string, so let's say if it's over here, we also want this to be as far as possible. So this distance over here is like, this is like a kind of a maximum distance that this can cover, and this over here is like a maximum amount of distance that this can cover. So in other words, if our first occurrence of X was like over here, then our next occurrence of X would have to like follow right after it basically. Because if there was some value of X, say for example, if there was a gap of like X and then there was like a random letter A and then X, it would always be strictly better to just, or I mean, it wouldn't be strictly better, but it would always be at least as good to swap this A and the X. And the reason why is that putting this X over here would ensure that we have one extra move that we would need to take, or I guess one extra inversion we would need to fix this initial string. And it's possible that moving this A over here makes it closer to its respective occurrence of A, but that's okay, because even if we essentially lose an inversion by putting A over here, we can guarantee that we gain an inversion by moving an X back. So doing this move will have a net total of like number of inversions to be either 1 or 0. So doing this will never make our answer worse. So that's kind of like a rough intuition on why grouping the same characters into one block is correct. And so with this observation, you can simply just do a little bit of a brute force. So because there's you have at most 4 distinct characters in the string, we want to check all 4 permutations of these like blocks. So it's 4 factorial. And then for each permutation, you want to check how many inversions it has. And so this is a standard problem that, again, could either be solved in using a BIT, or you could use like this constant factor times n dp, whatever. It doesn't really matter. In my implementation, I used a binary index tree. So in my case, it would be n times log n runtime. So yeah, this is the runtime complexity for problem D. And because n is 10 to the 5, it's roughly 24 times 10 to the 5 times about 17. And this is roughly, what is this roughly? Okay, this is about 2.4 million. This is like 24 million, and it's like 50. It's like, okay, it's roughly 50 million. It's like 5 times 10 to the 7. It's actually like quite a bit less than this, but it's like, this is essentially like just a very rough estimate. And 50 million is generally okay for a 2-second time limit. So 2-second TL. So yeah, that was my explanation for problem D. And that's pretty much it for the problems that I solved officially. If you like this style of editorials, let me know. If you prefer the whiteboard editorial, then also let me know. I'm just playing around with a different format here. So if you would rather want to see me draw stuff using like a whiteboard, then I'm completely fine with that as well. Wow, okay. I haven't made a video in a really long time, so I'm just tripping on my words here. But yeah, either way, I hope you enjoyed watching me explain these problems. If you didn't find them informative, I hope you found them at least entertaining. See you next time. Peace.